I wanted to thank the organizers and Dr. Cruz to be invited to this beautiful place. I have to admit I've never visited Vermont. We actually have a house in New Hampshire, but we never came up to Vermont yet. It is really, truly beautiful, and I just wanted to thank the organizers. So I flew out from California last night, and we still have the June bloom, so the weather is very similar, a little bit cloudy and foggy. Yet, truly, it's not only the climate, but also what I'm going to talk about today is this heavy hydrogen or deuterium that we pursue as part of our medical treatment plans for various diseases. And those are actually very closely related to some very basic mitochondrial functions that Dr. Bush was talking about. Now, as a short introduction, people, or you might, for people who don't know me, I'm actually one of the twins of my medical diploma day, and I wish my mom was here because she could tell us apart. I never could. Because I always saw my brother, I never saw us together, so I think I'm on my dad's right side, and this is the day when I got my medical diploma in 1987 from the medical school where Dr. Albert Sangiorgi, the vitamin C guy, was working, and we had to wear like a belt which had either L, which was László, or F, which was for Frank or Ferenc, my brother, because the teachers could never tell us apart. And obviously this gave us a great opportunity to kind of play around with our identities, yet it was just the life of twins, identical twins, which were very hard to tell apart. Yet we are doctors. We both became doctors, and actually I'm the 9th physician in our family. And I'll tell you a little bit of a story about this. I was born in Hungary. It's a neighbor country of Croatia, which Dr. Bush was talking about. In 1962, and growing up in a communist country, obviously my big dreams were simply just to work in the US sometimes and just be part of this very advanced scientific establishment. And sure enough, one day when my dad was asking like what I was going to do with my life, I told him I wanted to be a physicist, and he didn't give me dinner. He sent me in my room, and he told me that once I decided which medical school I'm going to apply for, then I can come out and I can finish my dinner. And sure enough, as any family, you want to know what your kids are going to be doing. But if you look at my family history, you can see that the first doctor who was born in our family was born in 1895, and he was a family practitioner. This is my father, who was a pulmonologist, and this is me. I'm the 9th physician. This is my brother, and his son is also a doctor. Meaning that for me, being a physicist was not really truly an option, and I had to eat, obviously, but I had my big plans, and I was, once I finished medical school, I was going to work in science, and I was going to pursue some deeper knowledge in physics that can be used in medicine. Now, this is my father. He was the pulmonologist of our small town. And you can see he's looking at x-rays and a chest x-ray. Yet in the same time, while going to medical school, I was playing the drums in the rock band. I was sneaking into a Queen concert in 1986 in Budapest as a hot dog guy because I didn't have the money to buy tickets. So I was just, I was paying one of these hot dog car guys just to get me in. But anyways, I really had a good experience and a great learning experience in medical school simply because I have learned about disease enough to see where the challenges are. So I'm very thankful to my father that he sent me to medical school. But in the meantime, since Szeged, where I finished my medical school, is a college town, I could take courses in mathematics and physics, which was my real passion. So after finishing medical school, I started out as a scientist. I got a fellowship from the Hungarian Academy of Sciences. These are my parents in 1961, and you can see the determination on their face, how strong they were, just practically have kids who are going to be doctors. And my mom was always helping us with all kinds of conflicts with my dad, as in any family. So eventually she smoothed it out that I didn't pursue clinical medicine. Yet I think there's a good reason to listen to a scientist, physician, simply because we do identify challenges that need to be related to the bedside. I do feel great respect for physicians who actually deliver the information and treatments or integrative medicine when it comes to healing or taking care of diseases. Yet there's an interesting fact about deuterium, and I just wanted to ask if how many of you have heard or how many of you haven't heard? You heard about deuterium. So how many of you haven't heard of deuterium? Yeah, just last week. So I would say it's 50-50%. Let me tell you a little bit about deuterium, and then you will understand why is it so important when it comes to your health. Now, deuterium is a stable, heavy isotope of hydrogen. In the periodic table, we identify atoms or chemical entities based on their number of protons in their nuclei. Hydrogen has one proton and one electron is circling around it. It makes it the fastest ball, like a ping pong ball in medicine, meaning that it's participating in energy production and many other chemical processes, synthesis, organic material synthesis, during photosynthesis when it's attached to carbon dioxide, yet it has a heavy brother. It's a stable isotope. It's called deuterium, and they call it deuterium because it has a double mass or double weight, and it has a proton and a neutron, and it actually participates in chemical reactions just like hydrogen, yet it has a different behavior. Now, by definition, we look at deuterium as one of the stable isotopes and not really significant because it's not that many in nature. It's 155 in oceanic water. For example, that's the reference range of 1 million hydrogen atoms, but when it comes to biological functions, it actually has a huge effect simply because this is the only atom in medicine or in biology or in physics or inorganic chemistry that doubles the weight. It's practically a very devastating stable isotope when it comes to biological functions. And we know that, in fact, it breaks protein nanomotors in our mitochondria and elsewhere in our cells. And it disrupts water production and ATP synthesis. I'm going to talk about this a little bit in more details. Deuterium causes disease. We do know, and I'm going to show you data regarding this. And deuterium provided by the foods and water which is correlating with some of the slides that Dr. Bush was showing us, and I'm going to cover those topics. And it can be actually, but we are lucky simply because actually it can be measured in body fluids and organs, and it is measured even though we don't know about it, even though radiologists don't know about the fact that when they do an MRI, they actually look at proton resonance, which is compromised by deuterium. So indirectly, deuterium is measured millions of times a day, yet the biology of biochemistry is not known behind it, and I'm here today to talk about this deuterium isotope. So it's like you probably saw like weightlifting in Olympics, maybe, when these guys get stuck with the weight, they can't lift it. That's how proteins actually, or certain protein hydrogen bonds behave when deuterium get attached to them. So they can't really move. They get stuck. So practically biology is very much dependent on movements and reactions and kinetics, and deuterium heavily interferes with the process. So once a hydrogen is replaced by deuterium in our biological system, it's a very different game. So just to understand how this system works, I wanted to show you this movie. This is the mitochondria, and here you can see these proteins which pump, these are called complexes, which pump protons or hydrogens from food outside of the matrix membrane of the mitochondria. And you can see here the protons from food or hydrogen from food. They are bouncing around, and the ratio is 250 to 1. And as protons actually spin this nanomotor, which is actually just like a hairdryer's nanomotor or a hairdryer's motor, when they actually bind to this, the protons, the hydrogens, when they bind to this protein, they move around, and at any given time there are 12 protons, 9 to 12 protons on any of these proteins. And you can see this little short tunnel and the longer tunnel, which actually become accessible for protons when they move the nanomotor around. In the meantime, this shaft, this protein shaft, which is literally a nanomotor, this is how we call it, it actually moves these proteins in the static part, and actually they produce ATP. It's adenosine triphosphate. It's a high energy, well, it's a phosphate that is easy to break, and the energy that is yielding is great compared to the energy that is invested in its synthesis. And as you can see, this nanomotor is spinning very fast, yet if you would put or drop a twice as heavy proton or hydrogen, in this case deuterium, in this nanomotor, it will actually break this protein delicate structure, so the nanomotor would stop. So deuterium, being such a different as far as its weight and chemical properties, it's really a very critical stable isotope to understand when it comes to biology. And the reason for that is actually these nanomotors spin very fast. So let's see, if your car spins about 3,000 rotations per minute, what do you think the nanomotor is spinning? It's actually 9,000 rotations per minute. It's actually like a Formula One race car. So you have to be very careful what you put in your body and what you fuel these nanomotors with, because if your food, and I'm going to talk about this in more details, is not deuterium depleted, or the water that you drink is not deuterium depleted, these nanomotors will suffer. And as a result of that, there's going to be many health effects and many disease processes that may develop over time. Now, I just want to clarify first one thing that is very important about mitochondria. We know that hydrogen comes from food and oxygen comes from air that we breathe in, and actually this is what mitochondria uses to produce water. The purpose of mitochondria is not to produce energy. It's the primary purpose of mitochondria is to produce water. Now, what the mitochondria or the TCA cycle does with this water will allow mitochondria either to produce energy or ATP, or would allow animals to survive in the desert, for example, or in the oceans where actually water cannot be consumed because of the salt content. So practically the primary purpose and function of mitochondria is to produce water, and the water is produced by those protons or hydrogens that are falling into the matrix and the oxygen that is waiting there to capture it and actually produce water first. And then various enzymatic, and we use this for many different biological functions. For example, when you're running, you produce a lot of water and ATP, and this is what we call metabolic water. And this metabolic or matrix water is recycled in your mitochondria to actually make this TC cycle, Krebs-Engeldy cycle, spinning around and actually produce or provide protons for energy. Now, what you don't see, or is not as obvious, that all your nerve functions, all your coordination, all your senses, all your biological or biochemical functions, they actually depend on this nanomotor function. Each cell has about 1,000 mitochondria, and each mitochondria has about 1,500 nanomotors. So you can imagine how significant this energy and water production rate is. Based on the oxygen consumption, if a human being would lay down for 24 hours without moving at all, you would still produce, as a very base rate based on oxygen consumption, about half a liter of water. Once you get up, once you get out of bed, this will actually multiply several times and by magnitude. So a marathon runner would actually produce a hectoliter of water during the run and about 60 kilograms of ATP. It's not net production, it's turnover, but actually these functions are very critical for our nanomotor functions are very critical for our well-being. And I talked about the brain and autonomous nerve system, but actually healing, regeneration of your tissues. Whenever there is a need for biosynthesis, these proton-deuterium ratios are very critical. So truly, I think all the talks today come together at the end, and I'm very happy to be part of this knowledge base, simply because I think deuterium light and obviously toxins and toxic agents in the environment, they all interfere with this process, and I'll tell you a little bit more about how. So deuterium is practically like yourself with a heavy backpack. So obviously when you look at deuterium and its biological effects, you have to think about this very dramatic change in its weight and biological behavior when it comes to delicate protein nanomotors. In fact, at the 2016 Nobel Prize in Chemistry was given out for the function of these nanomotors, moving proteins that actually are blocked by deuterium. Now, this is what we call deuterium fractionation. I'd like to clarify what is deuterium discrimination or what is deuterium fractionation. Physicists use fractionation because one fraction of water is different in its deuterium content than another fraction of water. And you can see here the map of the United States and Greenland, simply just based on how deuterium is distributed in the vapor or in the moist. You can see that actually closer we are to the ocean and lower the altitude is, more deuterium is in the vapor. As we move inland and as we move north, or as we move upward or higher elevations, deuterium is fractionated, depleted. It's simply because when you look at the oceans, they constantly evaporate water, and the water that evaporates from the water will have less deuterium. That moves over dry land, and in the form of rain, it will water our crops, and the crops are deuterium depleted by physical processes. This is what we call fractionation or deuterium discrimination, because deuterium stays in the water phase when it comes to distillation or evaporation. Now, when water is condensed, again, in the form of rain, then we get deuterium-depleted rainwater. When it actually waters our crops and the organic material, when the crop or the green plant's grass is grown, actually it's grown if deuterium-depleted water is used and not agricultural kind of irrigation or agricultural watering systems are used, it is deuterium-depleted. So the very important topics that Dr. Bush was talking about also relates to this deuterium fractionation process of what we use in our agricultural processes to produce food. Now you can see as we move up to the north, and if we go upward at higher elevations, you can see minus 270 per meter. Don't worry about the numbers, those are for physicists. But actually from 0, which is the reference oceanic water, you can go below of deuterium content very significantly, about 20–30%, just simply using this physical process of depleting deuterium from different fractions of water. It's interesting because actually the Genesis Bible starts with this principle, because God is hovering over the waters in vacuum. That's the most efficient deuterium fractionation process. So I actually use the scriptures to teach for some of my biochemistry courses at UCLA simply because it seems that the textures might have known some of these physical principles that we are talking about or covering here today. Now, this is a map which shows deuterium in our drinking water and tap water. And it's very similar to the pictures that Dr. Bush was showing us. And actually, this deuterium content, it also relates to cancer as well as depression. So epidemics or epidemiological scale public diseases seem to match the antibiotic use, the deuterium content in tap water, and this study has been published from Oxford, and they actually relate deuterium content of water with depression susceptibility, and they named some of the mechanisms related to the serotonin-related neurotransmitter function of the central nervous system. This is from the University of Oxford, yet we know it's not only serotonin, it's actually the damage that deuterium delivers to these nanomotors, and that interferes with all kind of biological functions. So, and I put the references up there, so we're going to generate a PDF of this talk, so you are welcome to look up the information. So, actually my involvement in deuterium research started in the year 2000 at a Hungarian dinner party in Los Angeles, and it was actually a friend of mine who is involved in freighter shipping, so he's not a doctor, and he told me that he has the remedy that cures every disease, and it's deuterium-depleted water. I told him, whoa, wow, that's like what it is. So I was stunned. I was just like, you know what? Just drink as much as you can, buddy, because it seems like it cures everything. Now, funny enough, he wanted me to study this, because at UCLA I run a lab where we use a stable isotope labeled glucose molecule, and we trace it in biological systems. And so he wanted me to study deuterium-depleted water, and actually he brought some in my lab. All of a sudden, like 2 days later, he showed up and he brought me like a 6-pack of carbonated deuterium-depleted water. Why don't I study this? So I told him, well, I don't have time right now to talk, just, put in. It's, too good to be true. Why would you waste your time on something that just really not making much sense at that point? I had to reverse my opinion about this, like many of you would, obviously. But actually, he just put some water in my office, and with my boss. And a few weeks later, he was asking me about the results. And by the time we drank the water with my boss, Dr. Lee, it tasted good. I mean, the water was fantastic. It really was very good quality. So I told him, listen, can I talk to you for a second? First of all, I work, I need to have an IRB, a in vitro cell line protocol, and pharmaceutical companies pay me green for me to carry these studies out. I can't just study catch-up or whatever. I have some academic obligations when it comes to running my laboratory. So I told him, listen, buddy, give me $25,000 per cell line and we're set. And I figured he's going to go away. $25,000 for deuterium depleted water just to kind of play with it. It's a lot of money. I was wrong. He actually brought Dr. Gábor Somlyai from Hungary with his checkbook, and they wrote SIDMAP, the company I can't take money directly from anybody, so it has to go through the UCLA spin-off technology transfer system, but they gave me $75,000 because they wanted to study 3 cell lines. So I said, these guys are either crazy, to be honest with you, or they are geniuses. And the later was obvious very soon. So we set up a study, and it turned out actually Dr. Somlyai already wrote a book about defeating cancer using deuterium depleted water, but in college I was reading Playboy magazines, like any college guys, This book somehow missed my attention. So, so when he was telling me, like, this is his book, I was just looking at him, okay, well, just write a check and I'll catch up with you later. I was really behind him, so I was really just kind of, I was trying to have them as far as data, because I'm a data guy. I do run studies with stable isotope, label glucose. I mean, those are sophisticated biochemistry studies, and this is what I was going to perform in my lab for him. And sure enough, we did finish this study based on the funds that he gave us, and we published this in 2006 at the Harvard University. There was a metabolomics meeting, and so we presented the data because, surprisingly, the dose response of deuterium depletion as far as mitochondrial function or biological response goes was very strong, to my surprise. It was actually stronger than some of the cancer drugs that I have studied in the past or before this study. It was actually very comparable to pharmaceutical effects. So to me, it was a biochemical challenge to explain this. Yet the data was very interesting because actually fatty acid synthesis, glucose oxidation, they were all affected by deuterium depletion. And we used the oceanic range, we used 100 ppm and I think it was 50 ppm. So we scaled down on deuterium in the cell culture, in the water of cell culture, and the cells, well, not all responded the same way, yet they all had some biochemical response, and we knew deuterium depletion affects biological systems. So there was actually mitochondrial substrate oxidation that was affected by deuterium. It was, and it was actually very comparable with pharmaceutical drugs, and we knew that there is a cell-specific response. We now understand why. And surely, the data was very informative as far as showing the effects, yet the details and the differences in response was somewhat obscure at that time. And I figured there's something, here, there's something still to be understood. And obviously he didn't give me more money, so I just stopped thinking about this. You know how it is, money rules. So practically we presented the data, everybody was happy, so there was a biological effect, it was an anti-proliferative effect, and that was it. So I just want to show you some data. The MCF7 is a breast cancer cell line, you can see, and don't worry about the details, I just want to show you that when we actually depleted deuterium from 150 to 150 ppm, there was an increase, dose-dependent increase in complete glucose oxidation, and there was also an increase in labeling in glutamic acid, which is one of the metabolic intermediates or one of the products of the TCA cycle, and the labeling pattern was dose-dependently correlating with deuterium depletion, yet in the pancreatic cancer cell line, we actually saw an opposite effect, and at that time, we knew it's maybe a substrate-related matter, yet we concluded that not all the tumor cell lines respond the same way to deuterium-depleted water. So, it's, when you're a biochemist and when you look at clinical problems, and when you actually try to correlate it with very basic findings, then you just either have to spend a lot of time on this or just have to wait. You have to wait for a model or a disease or a collaboration that will explain that to you. And actually it came in 2010. So for 4 years, nothing really happened because we didn't pursue additional studies. Yet in 2010, in July, Dr. Marston Linehan called me from the National Cancer Institute, who runs the oncological, surgical, urological surgical program at the NCI, National Cancer Institute. So I was just surprised that I would get a call from the NCI. Well, I get calls because I'm kind of the go-to guy when it comes to biochemistry-related problems. Yet it was such a detailed description of this case that I wanted to cover this a little bit. So he was telling me about this patient who has kidney cancer, and they published the results before he called me. And this patient had the only genetic abnormality they could find in this patient's tumor cells was that there was a enzyme deficiency in the mitochondrial TCA cycle. It's called fumarate hydratase. Now, it's not only that the mutation was unique, but the patient died very quick, which is in hypernephroma, it's really not that common. So she died, I believe, in 6 months, which was very rapid, and they couldn't do anything about her condition. What was also very interesting is that once they injected her isolated tumor cells into nude mice, the nude mice died also very quickly because of the rapid metastasis. And just to understand how important this process is, in 1937, Dr. Albert Szent-Györgyi, who discovered vitamin C, he also discovered, and he was given the Nobel Prize for 2 other medical or scientific discoveries. One was vitamin C, the biological oxidation process, and also the catalysis is fumaric acid. Fumaric acid is an intermediate in the mitochondria and in the TCA cycle, and this is the acid that is formed from succinic acid that actually picks up, that carries this metabolic water that is produced in the mitochondria. So fumarate hydratase, the enzyme that was missing from this patient, was actually the enzyme that recycles mitochondrial matrix water. And you can imagine me holding the phone with Dr. Linehan in my office, and immediately I figured that, holy cow, this is the model that actually relates deuterium-depleted water recycling to cancer simply because that has to be the water. Because this water has to be different from any other environmental water source simply because it transforms these cells. And interestingly, more interestingly, Well, my grandparents knew Dr. Sanjurji back in the 20s, so my grandma was talking about him many times. So I was always, like, biochemistry was always my passion simply because of him and because of the significance of his Nobel Prize. And I think the most important part of his Nobel Prize is actually fumaric acid formation. And what happened in the, if you look at the TCA cycle, and then I started looking at, okay, let's wait a minute. So the TCA cycle we know is to produce protons. Actually, it's not. It's to recycle water that is formed in the matrix. Because if you look at the TCA cycle, over 9 reactions, actually 4 of them relate to water recycling or water exchange. So simply this cycle is, besides being a carbon oxidizing process, it actually harvests the hydrogens from citric acid, and eventually this hydrogen has to be hydrogen. It cannot be replaced with deuterium because that will break the nanomotors. So I figured that if this patient couldn't recycle her deuterium depleted matrix water in the mitochondria, that caused her very significant and advanced cancer as far as clinical progression goes. And sure enough, if you look at this type of cancer, which is, it used to be called hypernephroma, now they call it clear cell renal cell carcinoma, simply because it looks like clear cells, because when water is not recycled in mitochondria, it actually ends up in the cells. So you're going to see these big, patchy, water-containing cells with significant mitochondrial degeneration, simply because water is not recycled, water is not consumed by these cells, and this beneficial metabolic water, which we'll talk about why it's deuterium depleted, is not benefiting her cells, so they turn into cancerous cells. Now, restoring fumaric hydrogens, so next what Dr. Linehan did, they actually fixed this problem in the patient's cells. So the cells that were actually causing cancer in patients now fail to produce tumors. So once they fixed this one problem, and that's nothing else but water recycling in the mitochondria, actually cured this patient's cancerous phenotype. So those cells were not able to produce cancer anymore, and the nude mice were not able to grow cancer if the wild type or the fixed same tumor cell line, yet with the fixed mitochondrial activity or water cycling reaction, was introduced back into the mice. So, and we wrote a paper about this, and before that I just want to cover some of the functions of the mitochondria. It's actually 3 different systems. Usually they look at mitochondria as one. No, it actually performs 3 different functions, but they actually happen assist each other. And obviously mitochondria is the cell organelle where actually most of your DNA deuteration, size of your DNA, cellular DNA, and energy production happens, yet there's a citric acid cycle or Krebs cycle or Krebs-Sanjurji cycle or tricarboxylic acid cycle. There's many names for it, but the most important aspect of it is actually a proton or hydrogen harvesting system. The hydrogen, which you can see here, is taken to one of these complexes of the mitochondrial membrane, and they actually pump these protons out to the matrix intermembrane space, which actually surrounds the matrix. These protons and certain gradient, they can only come back through these nanomotors, the nanomotor that I showed you. And they spin these nanomotors at 9,000 rotations per minute, and ATP is synthesized. One, the hydrogen gets into the mitochondria, the oxygen is waiting for it, and it captures it and forms water. Now, this water in the mitochondria is recycled through this fumarate hydratase, the enzyme that Dr. Sanjurji described, and the enzyme that was missing in this patient. So the cycle can turn over again, and recycling the same water produces another mole of ATP. So this is simply like a well-oiled and well-lubricated engine that actually uses this nanomotor physically to spin it and produce ATP energy for us. But the key to understand how it works is actually this water recycling system, because that keeps the cycle going. So looking at these three different main functions of the TCSI or mitochondria, eventually breaking this nanomotor can cause a number of significant problems in our metabolism. First of all, if the nanomotor is broken, protons cannot come into the matrix, hydrogens will pile up, and eventually the citric acid will stop. This is what we call the Warburg effect. The Warburg effect is even when oxygen is present, the nanomotors and the mitochondria are not working. And then your cells start producing ATP and energy through glycolysis or single carbon cycles. I'm not going to go into details, but practically in the presence of oxygen, tumor cells, and this is what Warburg said. Warburg didn't say anything other than in tumor cells, even in the presence of oxygen, the product of glycolysis or product of glucose is lactic acid. Simply because lactic acid is piling up when pyruvic acid is not consumed up by the cycle. And if the nanomotors are broken, this cycle is not going. So these cells adapt to a different metabolic environment or a different scenario when their mitochondria are not working, then they start using alternate energy production systems. It has very many very serious consequences as far as our cellular functions go. But simply, our paper that we published with the National Cancer Institute after finishing the study with Dr. Linehan, we were actually pointing out that in this patient, because of the lack of water recycling, there was a deficit in energy production, and there was a deficit in reducing power, simply because her cycle started the other way around. It started spinning not in the oxidative, but in the anabolic, or in the, we call it reductive carboxylation, the process. So you can imagine when your car engine starts spinning the opposite direction. That can cause a lot of problems, obviously. So that's what happened in her case. And we actually described, we published this in the medical literature. And simply, this step was the key to link Dr. Shomiai's deuterium-depleted water treatment with our own biochemistry and physiology, showing that actually our cells produce deuterium-depleted water, which has less deuterium. And this deuterium-depleted water is key to our cell differentiation. If we are not able to recycle the deuterium-depleted water that is produced from food, then surely enough, a number of medical problems will occur, including aggressive cancers. So then the FDA become interested in this. Obviously, this is a work order from the FDA. My company had to do this study for them. So they were looking at toxic effects of agents, for example, chemotherapeutic agents. And sure enough, one of their criteria was, maybe you can't see it from far, that compromised deuterium-depleting hydrogen exchange reactions in the mitochondria. We had to show this to them. So the FDA now is very alert about mitochondrial functions, and in some drug toxicity scenarios, they actually pursue this biochemical surrogate system that we can actually use to measure deuterium depletion in cells and also in the human body. Now, as I was mentioning, in 2016, the Nobel Prize for Chemistry was given out for these nanomotors and proteins that actually perform and harness energy from food. And these discoveries eventually are leading to the point that they all depend on this matrix deuterium-depleted water to function. And I'm not going to go into details how gluconeogenesis, the malic acid shuttle, the citric acid shuttle, eventually every source or substrate that goes through mitochondria, for example, fatty acids synthesized in our body, should go to the mitochondria through citric acid, so it has to be deuterium depleted. If we eat fat from animals that are grain fat, our fat deposits may become deuterium saturated simply because they actually kind of go around this mitochondrial deuterium depletion and water exchange process. So eventually we have a number of problems when it comes to interfering with mitochondrial systems, yet these protein nanomotors do the water recycling and also the proton harvesting and proton distribution process, and their structure, their conformation, their function, their kinetics, you know, it's different. If we give them, like, imagine somebody's juggling and then all of a sudden you give them a twice as heavy, like, ball, then they just gonna lose the dynamics of what they've been doing. Simply, this is what this difference in mass and weight of these proteins on these proteins is really hard on these proteins. So when we look at the functions and how deeply they are involved, breathing, moving, maintaining health, and discovery and recovering from illnesses, they are all depend on these nanomotor functions. And I was telling you, there's actually 90,000 protons transferred in the mitochondria per minute. That's actually 1,500 per second. So you can imagine if you would allow a natural deuterium abundance to run your nanomotors of 1 million of 150 deuterium in 1 million protons, which is actually 1 proton for every 6,600 hydrogens, running at the speed, actually you can break a nanomotor in every 4 seconds, 4.2 seconds, if you don't watch your deuterium content. If you don't allow your biological system to deplete deuterium sufficiently. So because of this very rapid transfer of protons, it's actually a very good filtering system also to filter out deuterium from a hydrogen cloud or water source. And this is what bacteria do. When Dr. Bush was talking about, because bacteria learned how to use this nanomotor to the opposite direction. And I'm going to show you how it works in a minute. But actually, these systems interfere very closely. So our gut microbiome or our bacteria is actually to filter out deuterium. So when Dr. Bush was talking about, I almost stood up and I always ask him, what do you think of those tissue-bound bacterial functions if actually breast cancer is growing faster when it's sterile? Because bacteria in tissues in the gut is to actually filter out deuterium using these nanomotors to the opposite direction. Because the physical process of like 4% less deuterium in, for example, in water vapor is too slow of a process. Our biological systems had to develop or collaborate with biological systems, for example, bacteria or viruses that actually can do this process much faster. And they can actually completely deplete deuterium because of these filtering mechanisms that are related to the mitochondrial functions. Because our body, our mitochondria, our nanomotors and proteins, they do everything they can to actually filter out or gate out or discriminate against deuterium. They would not allow deuterium get into our mitochondria. It's our food and it's our lifestyle that is, and global warming, well, climate change, better to say, it actually interferes with these processes. So overall, laying all these talks, and I'm looking forward to Dr. Cruz's talk because he will talk about resonance, which is a very important part of this biochemical establishment. So, so we covered this. When there's more deuterium, there's less energy, there's a phenotypic or there's a metabolic profile change as far as how cells adapt to higher deuterium environments. They have biological mechanisms to filter out deuterium, but it can be exceeded, it can be saturated, it can be overloaded, it can be destroyed in certain ways. So obviously finding the balance of your deuterium and biochemical functions or physical exercise and so on, you can actually balance out the very functional details of how this deuterium depletion works. And we have a clinic, Center for Deuterium Depletion in Los Angeles, and we actually have athletes and patients who actually have response to various deuterium drinking and feeding protocols. So, and this is practically a water molecule. I'm just, don't get lost with the numbers, but actually the oxygen-hydrogen bond or oxygen-deuterium bond is different. And we can see this in using various technologies. Isotopic discrimination fractionation actually starts with photosynthesis, because photons can easier break this oxygen-hydrogen bond from water than actually break the oxygen-deuterium bond. And it's because of its resonance. It resonates differently. And simply because of these small changes in resonance, there are specific biochemical alterations that relate to, for example, photosynthesis. Because photosynthesis is nothing else as breaking water from groundwater in trees. Hydrogen is attached to carbon dioxide, and carbon dioxide with the hydrogen is used for biosynthesis. The cow eats the grass, we eat the cow, and everybody's happy, yet the cow has to eat grass. It's the farm-raised animals. We have to live in our natural biological surroundings. My dogs sleep on the bed. I don't. Okay, I'm not ashamed of it. I mean, we just, it's just part of I can't imagine like going anywhere without my dogs. It's just practically just, yeah, it's just, I mean, we so much appreciate, the natural environment. Actually, be honest with you, when I actually pick up the poop in the backyard, the doggies, I do it barefoot. I do when the sun is out. And I do it with like less clothes on. I'm not going to show how I do it, but it's practically, that's my best time, practically. It's just soaking up the sun, just, getting contact with the ground and just, collecting doggy poops. I don't, that's part of our life. That's just part of our everyday life. And I don't let the gardener do it, because he would, no, that's my job. Every day I do this. So we have two dogs. One is a German Shepherd. He's the dumbest dog we ever had. Honestly. He doesn't even know what to do with breakfast. He's just looking at it. I'm like, buddy, you bite it, and it takes him half an hour to eat breakfast. But the German Shorthair Pointer, oh yeah, he's fast. But anyhow, so actually when it comes to deuterium, and many doctors would not know this, actually deuterium is the most abundant inorganic element in our plasma. When you go to the doctor, let's measure like calcium or magnesium or sodium, potassium. No. Those are actually the fraction of what deuterium there is as far as millimole per liters go in your plasma. It's actually the most abundant. So surely keeping this under control by food and nutrition has a very important element or very important aspect of understanding health and disease. So when you get started on deuterium depletion, you can actually see this with using any of these analytical methods. We measure deuterium in urine, saliva, and breath. Isotope, I'm not going to read them out because those are these ugly technologies, yet the proton resonance imaging, or MRI, might be something that you might want to hear a little bit more about, because that's a indirect deuterium measuring device. For example, here's a coconut. This is a transverse section, a 5 millimeter of a mature coconut. And when you talk to a doctor and they tell you, a radiologist, and they tell you actually it measures water, that's not true. Because here's the coconut water, which is actually darker, image on a T1 sequence, on a 1.5 Tesla T1 sequence. But the fat, the pulp, that's the brightest. That has the least deuterium in it. So fat in plants, fat in animals, fat in your skin, fat in your abdomen. They all have less deuterium than your water. And you can test this. That's what radiologists look at every day, many times. Now, this is the pop here that, you know, when you go to Hawaii and you buy this little plastic bag of little coconut pop, that's the white stuff here. And the coconut water that you drink, and it's it's actually not good for you. You know why? Because that has 155 ppm deuterium. So you should not, well, I'm not saying you shouldn't or shouldn't, you can decide this, but obviously using an MRI image, you can tell what's the deuterium-hydrogen ratio or density. It's not you cannot really see deuterium. This is how MRI works. It actually makes these hydrogens kind of, you know, bounce out of the magnetic field, and when they return, they emit certain frequencies, radio frequencies. But if you put a deuterium here, it actually stops these hydrogens from resonating. We call this tunneling effect. It's physics, so I'm not going to go into details, but actually if you put one deuterium here, 100 protons or hydrogen around them will stop moving. So practically, when you look at an MRI picture, you have to be aware of the fact that deuterium compromises the signal. So whereas there is more deuterium, there's less radio frequency emitted back by hydrogens using certain sequences, so you need to be aware of this. How do we know this? We measured it. This is an egg, and this is the egg yolk, and this is the egg white. We know the egg white is proteins, the egg yolk is fat, mostly fat. That's the yellow stuff. And sure enough, if you look at the light intensity of the egg and white, these are 1, 2, 3, and you actually compare the deuterium content of the egg white and the egg yolk, then you're going to see the same ratios as far as what the light of an MRI image tells you, or the density, light density, or the color composition, what an MRI picture will show you. It gives you exactly the same number as what we measure as far as deuterium content. So practically when you look at an MRI, or when you look at tissues and organs, looking at proton spectra, you actually look at proton and deuterium ratios in tissues indirectly. Now, that's when it came to us that can we use this as a clinical tool to actually measure deuterium and proton image density if we can measure deuterium using these methods. And sure enough, if you look at this liver cancer here, this has been published in the literature, you're going to start seeing these darker image on MRI, and this is how they actually diagnose, for example, in this 1.5 Tesla T1 segment. This is a paper from one of the radiology departments in the US. So you can actually see that the density or the image of a tumor is basically distinguishable simply because of the difference in density and light of the liver tissue in this case. So although it cannot be seen directly, it can actually be used as an indirect marker of mitochondrial functions, and you don't want your tissues to be deuterium enriched or saturated simply because your ATP synthase and your nanomotors will be affected by the process. And this is because deuterium has a very strong, which we call kinetic isotope effect. I'm not going to go into details. And this tunneling. Tunneling is like, you can imagine like playing football. You know, when the quarterback holds the ball, everybody's running, you know, down the field. That's tunneling effect. So once you actually move one atom or one player, all the rest of them start running to the same direction. That's what we call in physics tunneling effect. If you move a proton in a chemical bond one way, then all the other protons will arrange the same way. They move the same direction, and then they move back. So this tunneling is practically the basic element of chemical reactions, and is the basic element of MRI. And this is what is really compromised by deuterium, because if you put that's why they put those heavy players in the defensive line. You know, the game, when you actually attack or you defend yourself, you use different masses. That's simply how biology works. So deuterium there is practically to perform certain functions where you cannot really exceed a biological threshold, because you're going to be compromising some functions that are really related to hydrogen spin and tunneling and movements. So these have to be very carefully considered, both as people or friends who are actually interested in health, or physicians who actually treat patients, because diabetes, cancer, autoimmune diseases, and other chronic conditions are all in the rise and at alarming rate. What I didn't tell you, my twin died in 2006 of esophageal cancer, unfortunately. He was 44 years old. And sure enough, we are identical twins. I ran to Kaiser, my friend who works there. I told him, listen, we have to do a gastroscopy, a colonoscopy, because my brother died. We just buried him in September. And sure enough, they diagnosed me with very advanced esophageal hyperplasia, practically. So, you know, they were discussing certain options, and I told them, listen, I probably know better what to do. So I started depleting deuterium. In 2011, because of an umbilical hernia operation, I had to go through a workup, and they found a tumor in my right chest. And the radiologist told me, oh, you have to go and see an oncologist. I said, I don't think so. I just don't. Why would I? I know what to do. I deplete a little bit more deuterium. I went on a different diet. I started using different deuterium depleted water scenarios. So I'm still here, you know, happy as a clown. So I'm really not into standard medical care. I definitely wouldn't talk to an oncologist when it comes to standard care. I'm very happy to discuss deuterium with them, but not, you know, chemotherapy. That's how they cured my brother. So I'm very alert and actively studying this field simply to help myself and to help others. I do 30 push-ups every morning. I walk my dogs. And, you know, and I eat fat. I only eat fat mostly. I have coffee in the morning, and then I eat a few pieces of bacon, maybe egg yolk, and that's pretty much it. Maybe I eat a big steak, a big fat steak, when I feel like it, with some greens. So truly, this lifestyle deuterium depletion is working for me, and hopefully we can help others, and we do have a very broad range of diseases that we are treating with deuterium depletion. So we know deuterium is abundant in carbohydrates. It's simply because they are synthesized differently than fat in nature. I'm not going to go into details. If you are in a high carbohydrate diet and you don't eat enough fat, then you may develop disease. It's just simply because of the substrates. Those nutrients have very different deuterium content, and once you oxidize them back into metabolic matrix water, your mitochondria may be affected. Now, your body glycolysis, for example, is one of the most efficient deuterium depleting set of chemical reactions if you consume deuterium depleted water. Why? And this is why my students, when I teach biochemistry, they are always like, why do we need 9, 10 chemical reactions to break a 6-carbon glucose into 2, 3-carbon substrates, which is pyruvic acid? And I tell them, listen, I know it's aldolase could do it, but it's not about cleaving the 6-carbon sugar moiety. It's actually to replace every hydrogen, which has glucose has 12 hydrogens, and before they get to the mitochondria, they all have to be checked by our biological system not to have deuterium, which can use glucose as a Trojan horse to travel all the way down to mitochondria and bam, just practically burn it. So truly, if you kind of work as a biochemist and you look at the complexities, then you may learn about complexities through simplicities, and simply that's when my students appreciate introducing them to the deuterium story, because all those triose phosphate, hexose phosphate isomerase reactions, which actually occur through equilibriums and actually exchange protons on carbons. It's not one proton jumps from carbon 1 to carbon 2. No, it's actually dropping the proton into cytoplasmic water and picking up a cytoplasmic water, a hydrogen, to attach it to the same carbon. So practically it's a hydrogen deuterium exchange system, and this is why it takes so many steps, because that's how many hydrogens we have in a glucose molecule. And even though it's just one out of every 6,600 hydrogens, our glycolysis will still check it, because simply it's the damage that deuterium deuterium atoms or ions deliver, it's way too unproportional to how the weight difference is. It's practically 8, 10, 15 times more or harder to break a deuterium bond than a hydrogen bond. So the isotope effects are very significant. So based on the Vienna standard, these are deuterium content of certain food, and at my end of the talk you can actually register and actually get more details of these, of what kind of food we eat or you eat and what deuterium to expect. You can actually see that unsaturated fat and plant double bonds are actually only 102 parts per million, but actually there are lower deuterium contents, and probably the peroxisome and the mitochondrial axis is actually helping to harvest those very low deuterium double bond fatty acids. Instead of beta oxidation, which happens in the mitochondria, peroxisomes can actually modify chains, break fatty acids at double bonds, and harvest those low deuterium protons, and then they exchange the reducing equivalent with mitochondria. So this is a very interactive system. I'm not going to go into details because it would be too far from our scope and too long. But yet, when you go from white flour, you can actually see it's 155 ppm, then table sugar, then cottage cheese, and olive oil. Butter, which is now fat, is like down to the 124 ppm. Fatty acid and animal fat, and 118 ppm. Would anybody guess how much Crisco hydrogenated industrial oil, which you fry your chicken in? How about chips? That comes from GMO corn fiber. It's actually higher than 155 ppm. So you're actually eating industrial food. You can actually load your system with deuterium pretty heavily, and we measure these. So the way I know these is because we measure these. So we can actually give you some more information about that. So the depletion of deuterium is very critical in our body fluids. We actually measure these using various methods, and there's one function of our center is practically to deplete deuterium. Now, what kind of protocol you need, it depends on your measurements and phenotypes, but we can actually help you with information. We can use various body fluids. Breath is one that comes from your lung tissue and your body. Metabolic activity these are surrogate markers. We don't really know exactly the deuterium content of your tissues, but we actually know how much lower it is than what you see in your urine and your saliva. We actually treated collectively now over some 6,000 patients. Those are previous studies. We retroactively extracted their data from the literature, and we have published over 80 papers in the field, not necessarily discussing deuterium, but the biochemical processes lead to deuterium depletion one way or another. And our mission is to train clinicians, to have patients and people who are interested in deuterium fractionation and discrimination. Now, we use a we use a Brady test. You can actually test deuterium in your body fluids and your breath. There's a ratio there. It has to be a desired ratio, clinically very relevant. or we can test deuterium in your water and your food. So if you have water samples, you're not sure, if you don't know what you're eating, send us a little sample and we measure it for you. And we position your nutritional protocols based on what we find. So historically, deuterium goes back to the 1980s, where actually they showed that if we transfect human cells with the bacteria or ATPase or ATP deuterium filtering machine, and that retains deuterium in bacteria, they start dividing. In fact, they turn into cancer cells. And this was published in Nature in 1988. Sure enough, deuterium cannot pass through these nanomotors. It has been studied many times, and Gábor Somlyai, who actually brought me his check, who brought the check in his lab, in my lab when I was doing studies, he actually showed that deuterium in water actually regulate naturally occurring deuterium is very essential for cell proliferation. And it was published, so actually he pointed out back then in 1993 that deuterium depleted water significantly decreased the growth rate of these tumor cells, of these fibroblasts, and also inhibited the tumor growth in xenotransplanted mice, pretty much behaved the same way as the patient from the National Cancer Institute. So those cells which were treated with deuterium depleted water, they lost their phenotype, they lost their cancerous phenotype. So these publications go back far enough, yet we were able to link deuterium depletion with mitochondrial functions and with matrix water functions. So, and there are many biological effects. Because we don't have time, I'm not going to talk about these in details. These are my collaborators, Dr. Q. Collins and Gábor Somlyai. They are part of our clinic. Dr. N. Cooper treats patients. Esther Boros, my niece, she does all the informatics, and Dr. Paul Lee was my mentor at UCL and Agi Hirschberg. We started CIDMAP together, and she has been helping us tremendously. So for more information, you can go to signaturehealth.com. C is with a C. And if you want to know more about deuterium depletion, you can just text. You can just fill out the form. Depleted is a capital D. And then you can actually get more information about deuterium depletion. And with that, I thank you for being here, and thanks for your time.